Okay, welcome to Chapter 2, Section 6, talking about graphs of basic functions. And so we open with our discussion mentioning the concept of continuity. And the idea of continuity extends into calculus, and the proper definition that requires calculus. But for us, a very simple algebraic definition of continuity is just it's an interval where we can draw the graph without having to lift our pencil off the paper. Basically, the entire function would be defined there, and it would be a single smooth line of some kind. Now, it could be curved, it could be straight, it could be a squiggle, but as long as it remains connected throughout that interval, we can say that it is continuous. So they've given us this example, and you can see that there is some break in my graph here at 2. And that break right there represents a discontinuity, which is a point where your graph is not continuous. Okay, so basically, wherever you see a break in your graph, you can mark that section as being discontinuous. Okay, and the first examples that they present to us are just asking, hey, where are these graphs of functions going to be continuous? So looking at part A, you can see that this graph is always continuous. It never has a break in it. It makes that smooth parabola from being a squared function. So this one will be continuous from negative infinity to positive infinity. Okay. And this second graph, B, you can see has that open circle there, and that is going to represent a discontinuous point on our graph. And so that is going to occur at, of course, the number 3. And so we'll have negative infinity to 3, and then, of course, from 3 to infinity. Okay. And so, of course, that section, that 3 being discluded, says that, hey, at 3, there is some kind of discontinuity here. So that's kind of the baseline definition of continuity. And in an algebraic sense, that's kind of enough for us. Okay, so these next few sections are just going over some of the basic functions, their domain and range, and some very easy baseline points that we can use to graph them. Okay, so starting with, of course, the identity function, which is a linear function, and basically y equals x. And you can see the domain and range are both all real numbers, and it's always increasing. Then the second function we mentioned is a quadratic. The squaring function makes that parabola shape, and you can see that it both increases and decreases. It has its own intervals of doing that. So we can kind of mark some of the important points here. So the intervals where we increase and decrease, okay, are a little bit different and very important to note. And notice that both of these are continuous all the way throughout. Okay, what you will notice is most of our parent functions start out continuous throughout. However, there are some situations that are exceptions to that. Things where we divide, remember that we can never divide by 0, and that creates its own point of discontinuity. Okay, looking at a couple more cubic functions. Now, a good point to make is that cubic functions basically look exactly the same as any odd exponent function. So if you had something to the 5th power, like x to the 5th, that would be the same kind of appearance, even if the y values are a little bit bigger, it would be the same appearance as this x cubed, okay? And so you can see it's always increasing and it's always continuous. The square root function is one of the few where, we have a different domain and range. It is from 0 to infinity, and that's because we cannot take the square root of a negative number. Okay, couple here, cubic root. So any odd root looks like this, and notice that this one has a domain of all real numbers again, because we can take the cube root of a negative number. Okay, so odd roots actually have a bigger domain than even roots. Now, the one below it is the absolute value function. Now, we've talked a little bit about these before, and we're going to look at the absolute value function as an introduction to our next piece, which is talking about piecewise functions. Because the absolute value function has essentially two sections when we graph it, you can see that the first section is this piece going downwards, and the second section could be this piece coming upwards. And the absolute value symbol encompasses the idea that, yeah, we take the distance from 0, which means, of course, not including a positive or negative value association, only a distance value. And so negative numbers end up becoming positive, and positive numbers remain positive. So we can actually define this as two different rules, which is to say that if you have a negative number in the square root, you can flip the sign to make it positive. But if you have a positive number, you should leave it alone and not change anything. And so that definition is going to come up on this next slide. And this concept of using different rules in different situations is kind of what we use to create a piecewise function. So a piecewise function looks something like this here. And what it's saying is there are two sections in our domain and they both operate differently. So there is something we do if x is greater than 0, and we do something a little bit different if x is less than 0, which is if x is a negative number, right? So what we're saying here is if x is a negative, make it flip the sign. And if x is positive, leave the sign alone, okay? So basically, in piecewise functions, the first section here will tell you what math is happening to get your output. And the second section on the right will actually state what part of the domain it matches with. Okay, so this is the domain of that function piece. So let's take a look at an example down below and we'll see kind of what a graph of one of these will look like. So notice that we have two different sections in our domain. We have a rule for when x is less than or equal to 2 and a rule for when x is greater than 2. Okay, so what I'm going to do is I'm going to make two small tables and fill them with some numbers from the correct domain. So we have when x is less than or equal to 2. And so let's pick some numbers that kind of fit this category. So I'm going to start with x values like 2, 1, 0, -1. And I think that's probably enough for what we're trying to do here. And the operator with this is going to be this piece right here. So we're going to have -2x plus 5. So basically, I'm just going to plug these numbers into that, and we'll get out some outputs. So if you plug in 2, you should get back 1. 1, you should get back 3. 0 will give us 5. -1 is going to give us 7. Okay. Now notice, this section is a linear function. And so my graph for this piece should kind of follow that, and it should be a straight line. Okay. The second piece is also linear in this case. So if we want, let's go ahead and draw this piece, and we'll keep it in red just so that it's easy for us to connect which line goes with what. So let's graph 2, 1, okay, and then 2, 1, 1, 3, okay, 0, 5, and -1, 7. Okay, so you can see it is forming a straight line, and it's headed kind of like that. Okay, let's go ahead and do the same thing, but we're going to just graph what about when x is greater than 2. Now notice one thing, when I do this, I'm still going to start with my first number as being 2 for my x, and then I'll pick some numbers bigger than it. But there is something noteworthy about this, okay, and it is just that the first point, because I do not have the equals here, is going to be an open circle. Okay, so let's go ahead and x plus 1 each of these. So 2 becomes 3, 3 becomes 4, 4 plus 1, 5, and 5 plus 1, 6. Okay, so let's go ahead and graph this one, and we can go ahead and put this in. So 2, 3. Now notice this one is an open circle, and then 3, 4, 5, 6, so on. So there we go. We've got our line doing that. And so this graph shows you kind of a breakdown of the two. And the key thing here is, again, that this first point is an open circle. That's because of the domain of this section. Okay. So roughly, this is how you draw a piecewise graph. Do each section of the domain independently. Find the points that suit that section, right? So in the first one, I only put in values that were less than 2. So 1, 0, -1. And on the second one, where it was greater than 2, I had 3, 4, and 5. Include the cutoff point in both of them because you need to make sure that you're starting all the way from the most extreme value. Now, it can be an open circle or a closed circle, depending on what that domain looks like. Okay, let's graph one more of these piecewise functions. Now, this time we've got two sections of our domain, and one side, interestingly enough, is a quadratic. And it's going to change kind of how the graph looks. The other one is linear. So like part of this will be a straight line and part of it will be a parabola. Okay, so let's just start with the first section. Let's just start with x less than or equal to 0. And again, we'll make a little table. Let's use red for this side, x, and we're going to have 2x plus 3. And so again, I'm going to start from 0. Let's use some numbers less than 0, -1, -2, -3. And pick whatever numbers you're comfortable with. If you need more information, plug in more points. Okay, so 3, it's going to be 1, it's going to be -1, and then -3. Okay, so let's go ahead and mark this. Again, this one will be the filled in circle because I've got that equals with it. So 2x plus 3, let's do 0, 3, and then -1, 1, -2, -1, and so on. And so you can see the points are forming that straight line that we want. Let's go ahead and connect these all together. And we've got a nice line like that. Let's do the other half of this. So x is greater than 0. So of course we're going to fill this section with some numbers greater than 0. So how about 0, 1, 2, and 3? Okay, I've just been putting 4 points in this, but again, guys, if you're like saying, hey, I'm not sure what this graph is doing, or it's kind of going back and forth and you're not certain, make sure that you plug in some more numbers so that you can get the right picture. Okay, so let's see, this is going to be 3. We're going to have -1 plus 3 is going to be 2. -4 plus 3 is -1. And -9 plus 3 is -6. Okay, so let's go ahead and put this on our graph. So one cool thing is this one, these two connect together. So this open circle on top of the closed circle will just bubble it in. They're just connected together. Okay, but in reality, that filled in point came from the red section, not the blue section. Okay, and then we've got 1, 2, 2, -1, and 3, -6. And so as weird as this is a downward parabola like that. Okay. And so you can see this is quadratic on that blue section, linear on the red section. And you can actually combine the two and they connect and it forms this kind of continuous graph that we see. Okay. Now, some things to note. Piecewise functions are useful in real-world scenarios. Not everything can be explained by a single rule, right? And so when there are different rules to apply in different sections, piecewise functions are very handy in that you can have numbers less than 0 handled one way and numbers greater than 0 handled another way, or so on. And you could make a piecewise with huge number of pieces, multiple layers, to kind of explain more complex situations. Okay. All right. Last bit here, we've got the greatest integer function. And essentially what this does is that double bracket around the x is how you state it. And It finds a real number that is the greatest integer less than or equal to x. And essentially, in very, very layman's terms, it would be rounding the number back down to the lowest whole number. Okay. And so the examples they've given us, the greatest integer beneath 8.4 is 8, right? The greatest integer below -5, well, it's just -5. You don't have to round it down. There's nothing to it. Okay. Pi, 3.14, would round back to 3, right? That would be the integer that came before it. And watch out, this one's kind of the tricky one, that last piece, right? The integer that's less than 6.9 negative is -7, okay? Because remember, when you go to a bigger negative number, it's actually a lower value, okay? And so they've kind of shown how you calculate it, but the graph looks very interesting too, and we can see that on the last page here. And so this graph is sometimes referred to as a step function, okay? And basically, the reason it looks like this is all of the numbers in between get rounded back down to a certain flat value until you hit the next point. And then once you hit the next integer, that it jumps up to that next step, and then again they start rounding back down. Okay, so it's really interesting. It's got sections that are constant, okay, and it's got discontinuities all over the place, and it's just a very interesting function altogether. And you might imagine, hey, like, I've never had a function that could round off numbers, so to say, for me. And so this is a great way to express that idea. And it actually has one of the most interesting ranges that we will come across right here, okay? Which is that y is an integer, okay? Basically, the output is always a integer value, which means it has no fraction or decimal there, but it could be positive or negative, okay? And so we'll leave off there with that kind of interesting function. And there is actually a reverse of this, which is the least integer function, which is actually rounding the other way. Okay. But some cool thoughts to leave you with there. Okay. So hope this video was informative. Make sure you guys review over the behaviors of these different functions. This material is super helpful for what we're going to do next in chapter 2.7. Okay. Good luck and happy studying.